Hello and welcome, it's me Nathan, your friendly neighborhood support engineer. In today's video we'll be covering part 1 of a series of guides that cover our access points. Now in part 1 we're going to be covering the fundamental aspects of Wi-Fi networks, and we're going to cover a lot of general knowledge. Now I do not recommend you skip this video because it has a lot of important aspects to Wi-Fi networks that will help you save money and troubleshooting cost. Now we're going to go over some basics with Wi-Fi access points. We'll be talking about the 2.4 and 5G and what that means for Wi-Fi networks. We'll cover the different antenna types as well. We'll also be discussing what can affect your Wi-Fi coverage and talk about some general terminology such as channel distribution and MIMO or multi-user MIMO. Now when it comes to the 2.4 and 5 gigahertz frequencies, it is imperative that you fully understand what the pros and cons of each one are. This will set you up for ensuring that your customer gets the most out of every Wi-Fi installation you deploy. Starting off, we have the 2.4 gigahertz range, which oftentimes does have slower speeds, up to a maximum of 150 megabits per second. The advantage of the 2.4 gigahertz range, it just has a longer coverage range and a lot better penetrating power when it comes to material interferences. Now the one issue with the 2.4 gigahertz range is that it can be affected by household appliances, such as Wi-Fi fax machines, 1000-watt microwaves and baby monitors, and other devices that may use that frequency range. All in all, the 2.4 gigahertz is really good for both indoor and outdoor applications, or for clients who favor distance over max throughput speeds. Now when it comes to 5G, we can see up to speeds up to 1 gigabit. The only problem with 5G is it does have a shorter coverage range. Not as much penetration power through material interference, and there's a lot less devices, whether they're being used in a household or on business locations, that use the 5 gigahertz range, unlike the 2.4. So if you're ever setting up a Wi-Fi network for a customer that wants fast speeds as possible, you may want to have a greater overlap when it comes to the 5G network. Now when it comes to Wi-Fi access points, you're often going to find two types of antennas. We have a dipole antenna and an omni antenna. As you can see from these diagrams, the dipole antenna has a full 360-degree coverage range. Some dipole antennas can also vary between manufacturer. Some may favor a good vertical coverage range in the Z-axis, while others will sacrifice that to have a more meatier coverage range closer to the AP. That's why it's always important before you purchase, you make sure you know what type of antenna types you're buying. On the other hand, we have an omnidirectional antenna. The omnidirectional antennas are good for providing coverage ranges one side of the AP. These are great for bridge networks or APs that have to cover long hallways. This is probably one of the more crucial areas in which you may need to spend some time to learn what type of AP you need and what scenario. But for the most part, keep the antenna type in mind for your next Wi-Fi installation. Now, a lot of APs on the market might be rated with something called a MIMO or MIMO. Depends on who you ask. Tomato, tomato. This stands for multiple input and output. This basically means that one AP can have multiple antennas that can simultaneously both output and input information. Before the introduction of MIMO, most APs were considered half duplex, but with this technology, it allows full duplexing between capable endpoints. Now, it is important to know and understand the different types of MIMO, because even though that an AP might be rated for a MIMO, it might be a single user MIMO or a multi-user MIMO. So when it comes to single user MIMO, or just MIMO, the AP will operate in a mode in which it can have simultaneous streams between one endpoint. This allows for faster internet speeds between that one device. While multi-user MIMO shines when it comes to the Wave 2 compatibility of 802.11 AC standards, allows the AP to independently communicate with multiple devices at once. So if you're looking for a strong AP in a high density network situation, using an AP that supports Wave 2 multi-user MIMO is going to be your to-go-to option. Now one thing you'll see a lot of when talking about the multi-user standards is oftentimes you'll see a ×2, a ×3, or a ×4 in connection with the MIMO standards. A 2x2 is referring to how many antennas the AP has, and in that case it's going to be 2. 3x3 is 3 antennas, and 4x4 is 4 antennas. So with that logic, if an AP supports multi-user MIMO on Wave 2 with 4x4 technology, it could simultaneously use its 4 streams to communicate with 4 different endpoints at one time. Whereas a single user MIMO, or just MIMO, we'd be able to connect 4 streams to only one endpoint. Now, it is important that you note that not all endpoints are capable of utilizing the Wave 2 802.11 AC standards, so they may not be able to take full advantage of the multi-user MIMO function. With that being said, let's go ahead and talk about environment and material interference. Now, when it comes to environmental effects on Wi-Fi, certain objects will affect Wi-Fi over other materials, and it's important that you are familiar with this. If you know and understand the various materials that you're working with any Wi-Fi installation, it can help take some of the guesswork out of the equation, and you'll spend a lot less time running heat maps, which is a subject we'll be getting into in a later video. But as you can see from this graph, concrete, reinforced concrete, brick-faced concrete walls, brick-faced masonry block, concrete that consists of 102 millimeters, all have various effects on Wi-Fi decibel level. Other things like brick, masonry block, and lumber are less of an effect. Glass and plywood and drywall almost have little to no effect on your decibel level. Now, I know it may be confusing at first to look at the decibel levels and be like, well, what does that actually mean and how does that affect Wi-Fi? I'm sure when it comes to future Wi-Fi installations, you'll get pretty familiar with the decibel level, or what sometimes is referred to an RSSI value. But if I'm standing next to an AP and I have a decibel level of 10, my Wi-Fi connection is going to be great. Anything close to 0 is ideal. The farther away from 0 you are, you start running into the territory of degraded effects. So if I'm standing next to an AP and I'm reading 55 decibels, I can still get an internet connection, but it's going to be very slow and not reliable. Anything beyond 55 up towards the 70 decibel range, we're looking at almost unusable levels of Wi-Fi connection. Anything beyond 90, you're dead in the water. So if we were to put this graph into some use in a theoretical playground, just imagine if we had a wireless access point outside of a full concrete 203 millimeter thick concrete wall, we can expect to lose 55 decibels of penetration power between that AP and that wall. Meaning there's a good chance you'll expect some frustrations in connecting to the internet and get reliable streaming. If we put ourselves in the same situation with a concrete wall that is 102 millimeters thick, we might see a decibel loss of 26. There might be some degradation, but that's probably going to be a usable connection. And when it comes to glass or plywood, some walls aren't going to be a limitation. Now, in my experience, oftentimes you'll see the outside of houses that have stucco applied to the walls. Oftentimes, builders will use chicken wire to help get that stucco to stick to the wall. In these cases, chicken wire almost acts as a Faraday cage, blocking some of the Wi-Fi signals from getting through. So take in consideration that oftentimes you won't be looking at just a particular wall that's unidimensional, such as concrete. Oftentimes that concrete's going to have rebar, or maybe that wood plywood wall that we think is just drywall and plywood might actually have chicken wire behind it, which will limit those stable internet speeds. We'll be getting more into reading decibel levels and troubleshooting Wi-Fi speeds in a later video. Next, we have channel distribution. The best way I can describe channel distribution is it is almost similar to radio-controlled cars. You can have multiple people using the 2.4 gigahertz range, but on that range, there's a whole frequency range within that range that allows multiple users to both send and receive signals. As you can see from the diagram in the lower right-hand screen, we have channels 1, 7, and 13, and many different channels between those regions. This is how Wi-Fi access points can negate interference from operating between one another. The same is true for 5G, but one thing you might notice with 5G is that there's an indoor band and a section for indoor and outdoor bands. Some APs that are tailored for outdoor use have the added option to operate in outdoor bands with the capability of emitting a higher strength signal than what might be permitted indoors. The important takeaway from channel distribution is you never want neighboring APs to be on the same channel as your APs. Now, most AP providers, AP manufacturers, have built-in technology which allows APs to automatically change their distribution channel to avoid this level of interference. You can see that in the diagram in the lower left-hand corner, where we have all these APs presumably operating on either the 2.4 or 5G network that are operating on specific channels. As you can see from that example, every AP, whether in a mesh network scenario, or APs that aren't tied together, or are just on maybe a housing block, all are simultaneously operating on separate channels to avoid this interference range. There will be times in which you're going to do installations at some sites which are just completely compacted with multiple APs simultaneously trying to give out signal. There might be times in which you need to manually go into the AP and change its channel distribution manually. You can figure this information out by deploying a simple Wi-Fi scanner and picking up what's around you, and just choose the channel that's least populated. I would note that these channel ranges are going to be governed by the specific country in which you're deploying the APs at. So be careful if you're going to be buying an AP that wasn't originally sold in the United States or the country of your deployment, because there's a good chance that that AP may not be operable within that nation, within that country's environment. Alrighty, that goes for part 1 of Wi-Fi basics. The next couple of videos that we're going to be doing are going to dive in on how to fully install our APs from the general knowledge all the way up until doing the deployment, testing, and everything else. So please give a like on this video, subscribe to our channel, keep your eye on GS Tutorials playlist, and watch for more videos like this. And as always, my name is Nathan, and you have a good one.